Hey there! Here we go into volumes of solids of geometric cross-sections that are not from solids of revolution, meaning we're not getting our solids by revolving them. We're actually going to take cross-sections of them, like cuts of them. Very, very interesting stuff. Now, let me just point out that when you learn this in your calculus class, you don't actually have to be able to visualize what the entire three-dimensional object looks like. You don't. You do need to be able to basically visualize or draw out a rough sketch of what the cross-section looks like. So I'm going to go over that in this video, and really in each of the two videos that we're going to do for the lesson part of this. Let's jump into it. So it says the following region is the base of a solid. For the solid, each cross-section is a square perpendicular to the x-axis. Find the volume of the solid. So let's draw out the region, just like we've been doing in area, just like we did in volumes of solids of revolution. We got root x, and you've got x squared. And it's really only this part that we're looking at, right? Because that graph will continue on up like that. This graph will continue on like this. And technically x squared goes on like that, but we don't care about the left quadrant. We just care about this region right here. So now, we're talking about this region. You're taking cross sections perpendicular to the x-axis this way. So what do? Well, we do exactly that. We take a cross section, and I like to draw on a representative rectangle just like you're taking area. And it's crossed to this. So what this means is the base of this solid is going to have cross sections that are perpendicular to the x-axis and they're squares. Okay, what does that mean? Well, that means you basically have a square going into or out from this picture. So imagine it coming out of the computer at you. So I often like to draw on the rectangle like that, almost like it's a book, just to get an idea of what this thing looks like. You're basically now finding the area of this right there. And then you're going to multiply that area by a very, very thin change in x, or dx. So let's talk about this geometrically, right? Always let the geometry lead first. The volume that we're going after is equal to the area times dx, right? The area of that base times dx. Well, this part right here is this part right here. And since it's a square, we know that both this side length and that side length are congruent. They're equal to each other. So what's the area going to be? It's going to be that times dx. Well, this is just the height of the rectangle, which would be this curve minus this curve. So we're going to end up with this height right here. That height, or this height, whichever one you want to look at, is root x minus x squared, or top minus bottom. Now that's the length of this dimension. Since it's a square, this dimension is the same. So what's the area going to be? Well, that's going to be root x minus x squared times root x minus x squared, right? That'll give you the area of the square. Length times width, or base times height, times dx. And those are your three dimensions. Keep it as simple geometrically as you can. Now, what do we want to do to find the volume? Well, we've got to add up infinitely many of these very, very tiny books. And these books are going to change in size, right? As you get on in different parts of this region, you'll get different sized books. The height right here is going to be the same as the amount that this thing comes out of the region. So we're going to integrate from 0 right here to where they intersect there. Now, where do they intersect? Well, root x equals x squared. We're going to end up with x equals x to the fourth, squaring both sides. 0 equals x to the fourth minus x. So 0 will be equal to x times x cubed minus 1. Set each equal to 0, we'll get x equals 0 and x equals 1. 1 cubed minus 1 is 0, so that's what we're stacking to. We know that it's with respect to x because, again, they're taken this way, so you get a really, really thin change in x. So that's it. That's your setup. So we're going to go ahead and find the volume of this thing, but I want to make sure that you are in good shape on the concept. All right. In general, you're integrating the area of the cross section with respect to either x or y. If you're with respect to the x-axis, it's x. With respect to the y-axis, it's y. It just depends on which way you're stacking these things. Imagine putting lots and lots of books in a shelf, and that's from A to B. That's it. That's your general form. All right. That's the concept. So let's go ahead and let's integrate. So we're going to get the integral from 0 to 1 of, we'll FOIL this thing out, root x times root x is x. Root x is x to the 1/2 times x squared is x to the 5/2. You're going to get two of those, two minuses. So minus 2x to the 5/2. And then minus x squared times minus x squared is plus x to the 4th. Beautiful. Okay, now from here what we're going to do is we're just going to integrate, right? The concept we're leaving behind. Right? We finished that. This is to integrate. This is going to be x squared over 2 minus 2 times, this will be x to the 7/2, and then we've got a 2/7 there, and then plus x to the 5th all over 5. Thank goodness for the bounds, 0 to 1. When I plug in 1, I'm just going to get 1/2. I'll get 1 times 2 is minus 4/7. And this is going to be 1/5. So as gross as those numbers are, we're then only going to be subtracting 0 when we plug everything in. And so now what I've got is a common denominator of 35ths. Actually, no, 70ths. Ugh. So it's 35/70ths minus 10 times 4 is 40/70ths. Plus, this will be 14/70ths. Nice. And when we combine everything, we're going to get minus 5 plus 14 is actually just 9/70ths. That's not bad. It's a funky looking volume, but that is our answer. Not so bad. Not so bad. So that's our setup, though. Make sure you get that setup down. Okay, let's go to the next one. It says the following region is the base of a solid. For the solid, each cross-section is a square. Again, we know it's a square, perpendicular to the y-axis. So this time we're going this way. So the same exact region, like that. So we already know it intersects at 1, 1. We know that from the last problem. And 0, 0. And so now we're taking cross-sections perpendicular to the y-axis. So that's going to be this way. So now you got rectangles going right to left. So if you take a look at that, it's going to look like this. And you can go into or out of that object. Beautiful. And if you think about it, that height then is a very, very small change in y. So it's with respect to y. So we've got to solve both of these with respect to y. If I square both sides, that's like y equals root x. I'll get y squared equals x. If I square both sides here, I got to take a square root, that is. I'll get positive root y equals x. We just want the positive root since we're on the right side of the y-axis. Now, let's take a look at how we're going to find the volume. It's going to be the area of this that we want, all of that, which is this dimension times that one. Well, this right here is this piece. And so that we know is root y. This we know is y squared. So the distance between here and here, the positive distance, remember we want everything positive, is right minus left. So that's root y minus y squared. Since it's a square, we're told that it is. This is the same as that, right? That's a square. Might not look like it, but it is. So this will also be root y minus y squared. And you multiply length by width times height. So that's going to be root y minus y squared times root y minus y squared, nice, times dy. Now we want the volume of it, so we're going to integrate from, and it's actually still 0 to 1, but we're stacking bottom to top this time. And, well, there's no real reason for me to integrate that out by hand, because if you notice our last problem, it's the same exact setup. Right, now that's just coincidence. So if we integrate all of this out, we're going to end up with 9/70ths like we did last time. So the main idea here is not about how to integrate it. It's about how to set up the integral, as it's been in this whole chapter. Your number one idea here is that you want to find the area of your cross-section. You'll be told enough information to know what the shape is. So keep the geometry basic. It's a square. So I've got that squared, or this times that. And then to figure out what the dimensions are, put in your representative rectangle, and you can figure out the length of the rectangle just by figuring out right minus left, or in the last problem, top minus bottom. All right, I'll see you in the next video. We'll do some more shapes. We got some triangles, some rectangles, a semicircle. It'll be a good time. See you there. Peace.